It is the largest power station ever built, a wall of concrete stretching more than 2 kilometers across the Yangtze River, holding back a reservoir that runs for hundreds of kilometers behind it. It can generate more electricity than any other single structure on Earth, and its construction required relocating well over 1 million people. The Three Gorges Dam is, by almost any measure, one of the most ambitious engineering projects in human history. But for years, it has also been the subject of persistent questions about the quality of its construction, about its effect on the region's environment, about sediment piling up behind it, and about whether the enormous benefits it provides come with risks that have never been fully accounted for. Critics have even given it a nickname that is stuck: a Tofu-Dreg project, a Chinese phrase used for construction work that looks solid on the surface but is allegedly poorly built underneath. So how much of this is genuine concern, and how much is exaggeration? Today we are going to walk through the real debate around the Three Gorges Dam, the documented concerns, the official responses, what has been verified, and what hasn't. Because the truth here is more complicated and more interesting than either side usually admits. Let's start with the scale of what we're actually talking about. The Three Gorges Dam sits on the Yangtze, China's longest river and one of the largest in the world. Construction officially began in 1994, and the project came online in stages over the following years, with full power generation reached around 2012. The total cost is generally estimated in the range of tens of billions of dollars, with figures around the 28 to 32 billion mark commonly cited. The dam was built with 3 primary goals. The first was flood control. The Yangtze has a long and devastating history of flooding, with major floods in the 20th century alone killing enormous numbers of people. The dam's reservoir was designed to absorb floodwaters and release them in a controlled way, protecting cities downstream. The second goal was power generation. The dam's turbines produce a massive amount of clean electricity, displacing what would otherwise be generated by burning coal. And the third was improved navigation, allowing larger ships to travel further up the river through a system of locks. On those headline goals, the dam has delivered real results. It generates an enormous quantity of carbon-free electricity every year, and it has been credited with moderating several flood events on the Yangtze. These are genuine achievements that any fair assessment has to acknowledge. But the scale that makes the dam impressive is also exactly what makes its critics nervous. When a structure is this large and holds back this much water, the consequences of anything going wrong are correspondingly enormous. And that is where the controversy begins. The most attention-grabbing criticism of the dam concerns the quality of its concrete. During construction, the project poured concrete at a record-setting pace. In one peak year around 2000, the volume of concrete placed was several times what the famous Hoover Dam required across its entire construction. Pouring concrete that fast creates a genuine engineering challenge, because as concrete cures, it generates heat, and if that heat isn't managed carefully, the material can develop internal stresses, cracks, or voids as it expands and contracts. The Hoover Dam famously solved this problem by mixing its concrete with chilled water and running cooling pipes through the structure to control the temperature as it set. Critics of the Three Gorges project have alleged that, in the rush to set records and meet deadlines, similar temperature control measures were not applied as rigorously as they should have been, and that this led to cracking and voids in parts of the structure. These concerns are not purely the invention of outside critics. Some of the people involved in the project's own quality inspection process raised flags during construction. There are documented references to inspection teams finding surface defects, cracks, and seepage in certain areas, particularly around the ship lock system, where teams reportedly found voids in the concrete during the early 2000s. Internal correspondence from quality reviewers described the overall quality at the time using cautious, hedged language rather than glowing approval. Here's the crucial context that often gets left out, though. According to the same engineering records, those defects were identified and then remediated. Reports document that water-seeping cracks in the lock system, totaling thousands of meters in length across hundreds of instances based on mid-2000s surveys, were subsequently repaired to meet design requirements. In other words, the concerns were real, but they were also addressed through ongoing maintenance and repair, which is, to be fair, a normal part of operating any massive piece of infrastructure. So the honest picture is this. There were genuine quality concerns during construction, some raised by insiders, and there has been ongoing repair work since. Whether that represents a structure that is fundamentally sound but high maintenance, or one with deeper problems, is the heart of the dispute, and reasonable engineers have landed on different sides of it. In July 2019, a story exploded across the internet. Someone posted satellite images appearing to show the dam visibly warping and bending out of shape, sparking a wave of panic that the structure was deforming and at risk of failure. This is worth examining closely because it became one of the most widely shared claims about the dam, and it turned out to be misleading. The apparent warping in those images was not real structural deformation. It was an artifact of how certain satellite mapping services process images, automatically stretching and distorting flat imagery to drape it over three-dimensional terrain models. When you look at a long, straight structure laid over uneven terrain in those systems, it can appear to curve even when it is perfectly straight in reality. Other satellite images of the same dam, processed differently, showed no such bending. Chinese authorities responded by stating the dam was operating normally and within its safety parameters, and independent observers who examined the imagery agreed that the viral deformation was an image processing illusion rather than evidence of a failing structure. This episode is important for two reasons. First, it shows how quickly alarming claims about the dam can spread regardless of whether they hold up. And second, it's a useful reminder to treat dramatic claims in either direction with some caution. The dam has genuine, documented issues worth discussing. The 2019 It's Bending panic was not one of them. Beyond the structure itself, some of the most substantial debate concerns the dam's effect on the surrounding environment. And here, the science is genuinely complex and still debated. One area of concern is local climate. After the reservoir filled, the surface area of standing water in the region expanded enormously, by some estimates more than doubling. Some researchers, including geologists who have studied the area, have argued that this large new body of water altered local weather patterns, contributing to increased evaporation, shifts in temperature, and changes in rainfall in parts of the surrounding region. They point to a series of extreme weather events in nearby provinces in the years after the reservoir filled, including severe flooding in areas that had historically been prone to drought. A NASA-affiliated study using satellite data did examine the reservoir's potential influence on regional precipitation and surface temperatures, and found measurable effects on rainfall in certain areas near the reservoir. However, it's important to be precise here. Attributing specific weather disasters to the dam is scientifically difficult. The same years saw broader climate variability across China and the wider world, and separating the dam's local influence from larger regional and global climate trends is genuinely hard. So while the idea that a reservoir of this size affects its immediate microclimate is plausible and supported by some research, sweeping claims that the dam caused every flood or heat wave in the broader region go well beyond what the evidence can support. Other documented environmental concerns are more clear-cut. Sediment management is a real and ongoing engineering challenge. The Yangtze carries a heavy load of silt, and dams interrupt that natural flow, causing sediment to build up in the reservoir over time. Water quality changes in slow-moving reservoir water are a recognized issue, and there are well-studied concerns about reservoir-induced geological activity, where the immense weight of stored water and fluctuating water levels can increase the frequency of small landslides and seismic events near large reservoirs. These are not unique to the Three Gorges Dam. They are known challenges for major dams worldwide, but the sheer scale here amplifies them. One of the more thought-provoking concerns raised by critics involves not the Three Gorges Dam alone, but the entire system of dams now operating on the Upper Yangtze and its tributaries. Over the years, China has built a series of additional large hydropower stations upstream on the Jinsha River, which feeds into the Yangtze. On one level, this makes engineering sense. Upstream dams can hold back floodwater and trap sediment before it reaches the Three Gorges Reservoir, easing pressure on the main dam. But critics point out a less comfortable implication. Stringing many massive dams along the same river system creates a chain. The concern is that if any single dam in that chain were to fail catastrophically, the sudden release of its stored water could threaten the dams downstream of it in a cascading sequence. It's a low probability but high consequence scenario, and it's the kind of systemic risk that's genuinely worth engineers thinking carefully about. Not because failure is likely, but because the stakes are so high. It's worth stressing that this is a hypothetical risk, not a prediction. Modern dams are built with significant safety margins, and a cascading failure would require an extraordinary chain of events. But the more dams you build on one system, the more the individual structures become interdependent, and that interdependence is a legitimate subject for ongoing safety analysis. Part of what fuels skepticism about the dam is the series of expensive follow-on projects that have been built around it over the years. Projects that critics argue exist partly to manage problems the dam itself created. One example is the bypass system for shipping. Because traffic through the dam's locks can back up significantly, with ships sometimes waiting days to pass, authorities built an over-dam transport route. Goods are unloaded from ships on one side, trucked overland along a dedicated highway, and reloaded onto ships on the other side, bypassing the lock bottleneck. The highway portion alone reportedly cost hundreds of millions of dollars, and that's before adding the upstream and downstream port facilities. Another major project is a large water diversion tunnel, begun in 2022, designed to carry water from the Three Gorges Reservoir area through a nearly 200-kilometer tunnel to the Han River. Officially, this is framed as a follow-up to China's broader water diversion programs, aimed at maintaining water levels downstream. But analysts have noted it also serves another function, giving the dam an additional channel to discharge water during flood conditions, helping relieve the difficult balancing act the dam operators face. When a major flood hits, releasing too much water risks flooding cities downstream, while holding too much back risks flooding cities upstream. An extra outlet gives operators more flexibility in that trade-off. Supporters would frame all of this as sensible infrastructure that maximizes the value of a major asset. Critics frame it as evidence that the original project created cascading problems requiring ever more expensive fixes. Both interpretations describe the same facts, which is often how these debates work. Underlying all of these specific concerns is a deeper debate that goes back to before the dam was ever built. During the project's planning and evaluation in the late 20th century, it was not universally supported, even within China's own expert community. The environmental impact assessment process was genuinely contentious. Some experts argued that the ecological and environmental downsides of the project were serious enough to warrant reconsidering whether it should proceed at all. And there were disagreements about how the official conclusions were ultimately framed. This internal debate is part of the historical record, and it reflects something true about megaprojects everywhere. Enormous infrastructure decisions involve real trade-offs, and reasonable experts can disagree about whether the benefits justify the costs. That tension has never fully gone away. Supporters point to the clean electricity, the flood control, and the navigation improvements as transformative benefits for a country of over 1 billion people. Critics point to the displaced communities, the environmental disruption, the sediment and water quality challenges, and the ongoing maintenance burden, and argue the full costs were understated from the beginning. The most honest assessment is probably that both things are true at once. The Three Gorges Dam is a genuine engineering achievement that delivers real, measurable benefits. It is also a project with real, documented downsides and ongoing challenges that its operators have to manage continuously. Whether the balance comes out positive or negative depends heavily on which costs and benefits you weigh most heavily, and that's ultimately a question of values as much as engineering. Let's come back to the question in the title. Is the Three Gorges Dam facing a new crisis? The responsible answer is, not in the dramatic, imminent collapse sense that sometimes circulates online. The dam has now operated for roughly 2 decades. It has weathered major floods. The viral claims about it physically bending were debunked. There is no credible evidence that the structure is on the verge of failure. What the dam does face is a set of ongoing, chronic challenges that don't make for dramatic headlines, but are genuinely significant. Sediment accumulation that worsens over time, environmental effects on the surrounding region, the maintenance burden of a structure built at record-breaking speed, and the systemic questions raised by an entire chain of dams on one river system. These are real engineering and environmental issues that will require attention for as long as the dam exists. So rather than a single sudden crisis, the more accurate picture is a massive piece of infrastructure that delivers enormous benefits while carrying a long tail of complicated, slow-moving problems. Exactly the kind of trade-off that comes with building at this scale. What do you think? Do the flood control and clean energy benefits justify the environmental and engineering trade-offs? Or do you think projects on this scale create more problems than they solve? Let me know your honest take in the comments. This is one of those topics where thoughtful people genuinely land on different sides. And if you found this balanced breakdown useful, consider subscribing so you don't miss the next deep dive into the engineering megaprojects shaping our world.